Hey everyone, and welcome! Today we're going to put on our detective hats and step right into the lab. Our mission? To solve a classic chemical mystery. How do you figure out what a substance is when all you have is a pile of it? Let's get this investigation started.
So just imagine this for a second. You're a chemist, and someone hands you a vial filled with some mysterious white powder. You can pop it on a scale and find its mass, sure, but that's all you know. Is it sugar? Is it salt? Could it be something totally new? The secret to its identity is locked away in its chemical makeup, and our job is to crack the code. All right, first step, the mystery of the unknown compound. So what's at the heart of this whole mystery? Well, it all comes down to its chemical formula, that one crucial piece of information that we're missing. That's right. You can think of a chemical formula as a substance's own unique fingerprint. No two compounds have the same one. So for chemists, figuring out this formula is always the absolute first step when they come across something new. It's the foundation for understanding everything else about it. So where do we start our investigation? Well, like any good detective, we start by profiling our suspect. We need to figure out its percent composition, which is basically a fancy way of saying we need to find out what it's made of by weight. So the first tool in our detective kit is something called percent composition. And it's pretty much exactly what it sounds like. We're creating a profile of our substance by figuring out the percentage by mass of each element inside it. Is it 75% this, 25% that? So let's say we analyze an unknown gas. We find out that a 10-gram sample is made of 7.5 grams of carbon and 2.5 grams of hydrogen. Well, that means its percent composition is 75% carbon and 25% hydrogen. This is our first solid clue. And don't worry, the math here is actually super simple. You just take the mass of one element, divide it by the total mass of the whole compound, and then multiply by 100 to get a percentage. This gives us a really precise breakdown by weight. Okay, but here's where the case takes a really crucial twist. Knowing the mass breakdown is just a clue. Chemical formulas you see aren't about mass, they're about the number of atoms. So we've got to translate our mass-based clues into atom-based counts to really crack this code. This right here, this is probably the most important clue in the entire case. We have to make a mental shift away from thinking about mass and toward the number of atoms. And to do that, chemists use a unit called the mole. Just think of it as a word for a number. Like a dozen means 12, a mole just means a ridiculously huge number of atoms. It's our key to unlocking the formula. And the great news is there's a simple 3-step process we can follow every time. Step 1, we convert the mass of each element into moles. Step 2, we find the simplest ratio by dividing all the mole amounts by whichever one is the smallest. And step 3, if we get fractions, we multiply everything to get nice, clean whole numbers. All right, theory is great, but let's get our hands dirty with a real case, shall we? We're going to take a look at the mineral hematite. It's a really common type of iron ore. Let's see if we can use our 3-step process to uncover its formula. Okay, so take a look at the table. Our sample has about 35 grams of iron and 15 grams of oxygen. First, we convert those masses into moles. Now, look at that ratio column. To get that, we divide both mole amounts by the smaller number, which is the moles of iron. And that leaves us with a ratio of 1 iron atom for every 1.5 oxygen atoms. Now, obviously, you can't have half an atom in a chemical formula, right? So we do step 3. We multiply everything by the smallest number that'll give us whole numbers. In this case, that's 2. So Fe1O1.5 becomes Fe2O3. And boom, just like that, we've found it. This is the empirical formula, the simplest whole number ratio of atoms. Okay, that was a huge breakthrough, but hold on, we're not quite done yet. See, the empirical formula gives us the simplest ratio, but it's not always the actual formula of a molecule. To get the final reveal, the true identity, we need one last piece of evidence. So what's the difference? Well, think of it like this. The empirical formula for glucose is just CH2O, the simplest ratio. But the molecular formula, the true fingerprint, is actually C6H12O6. Our job now is to figure out if our simplified version is the final answer or if we need to scale it up. So how do we get from this simple ratio to the real deal? We need one final clue, and it's something we usually find through another experiment, the molecular mass of the entire compound. This number is the key that unlocks the true formula. And again, the final calculation is really simple. It's just a 2-step process. First, we calculate the mass of our empirical formula. Then we divide the real molecular mass by our empirical formula's mass. That gives us a whole number multiplier we can call n. Okay, let's go back to our CH2O example. Let's pretend we ran another experiment and found that the true molecular mass of our compound is 180 AMU. And by the way, AMU just stands for atomic mass units. It's just the scale we use for weighing something that tiny. Now we need to calculate the mass of our empirical formula, CH2O. So we just add up the parts. We look up the atomic mass of each element. Carbon is about 12, each hydrogen is 1, and oxygen is 16. So 12 plus 2 plus 16 gives us a total of 30 AMU. All right, this is the magic moment. We take the real molecular mass, 180, and divide it by our empirical formula mass, 30. And what do we get? We get 6, a perfect whole number. This n value, our 6, is our multiplier. So all we have to do is multiply all the subscripts in our empirical formula by 6. CH2O becomes C6H12O6. And there it is. We've just figured out our mystery compound is glucose. Mystery solved, case closed. Okay, so this might seem like a really neat chemistry puzzle, but why does any of this matter in the real world? Why do we need these chemical detectives? Well, this kind of detective work is happening all the time, everywhere. It's used to analyze fertilizers to make sure they have the right stuff to grow our food. It's used to confirm the exact structure of medicines like aspirin. It's even used to figure out the precise molecular formula of compounds like nicotine. It's absolutely essential. This whole process really is fundamental to how we understand, well, everything around us. Every single substance we know of has a chemical fingerprint. And it kind of makes you wonder, right? As we explore new materials and discover new things, what entirely new formulas are still out there, just waiting for a chemical detective to uncover them?